Okay, so we just, in the previous video, we got done talking about some of the basics of polynomial long division, and this was the last problem we did. And this problem here corresponded to the Desmos graph that we had over here. And what's interesting that we can say about the result of this long division problem is that because there was a remainder of 0 down here, it meant that x minus 3 divides this divisor, x minus 3 divides this large dividend, which is this fourth degree polynomial. It divides it evenly. There is no remainder left over. What do we say when we have a number that divides into another number evenly? Well, we say that that is a factor of the original number. So in this case here, we could say that 14 and 1,234 are both factors of this larger number here, 17,276. Well, in just the same way, we could say that x minus 3 times x cubed x cubed plus 4 x squared plus x minus 6, if we multiply those two together, those are both factors of this dividend here. And this is kind of an important distinction to make. So let's actually look into a little bit more into long division here. There's another situation that can come up, and that's when we're missing terms. Just because we're missing terms here doesn't mean that we can't do it. It's actually not a big deal at all. What you do in the event you have missing terms is that you just you fill in zeros for those. They're essentially, they work as placeholders. So x cubed plus 15 is the exact same thing as x cubed plus 0x squared plus 0x plus 15, because 0x squared and 0x are both 0, so I basically did nothing to that dividend. The reason this is important is because it serves as a placeholder procedurally for when we do long division. So let's do that real quick, actually. So x goes into x cubed, x squared number of times, and if you'll notice when I'm doing these, I tend to write, if I'm going to have an answer up here with x squared in it, I want to write that above where x squared usually is in the dividend. It just keeps things organized. It's absolutely not necessary, but I like to do it that way to keep everything kind of tabulated. So x squared times x is x cubed, and then x squared minus 3x, x squared times negative 3, I don't know what I'm saying, is negative 3x squared, and we just do the same thing we normally do. So if we subtract these, we'll get negative 3x squared here. Okay, now, if we take that x squared and sorry, one second. If we take that x squared and we multiply it we bring down to 0x. I'm skipping steps here. Bring down to 0x, we have plus 0x. Now we say, how many times does x go into negative 3x squared? It goes in negative 3x times. Okay, negative 3x times x is negative 3x squared. Negative 3x times negative 3 is positive 9x. Okay, we do a subtraction. 0, it's going to be 0, this is 0, and then 0x minus 9x is negative 9x. And then we bring down this 15, so we have plus 15, and we say, okay, how many times does x go into negative 9x? It goes into negative 9 times. Negative 9 times x is negative 9x. Negative 9 times x, negative 9x. Negative 9 times negative 3 is positive 27. And then when we do that subtraction, we will get an answer 15. Basically, this is going to be 15 minus 27, which is negative 12. Is it negative 12? Yes, negative 12. So here's an example where first we had two things happening differently. We had to put in these placeholders, and we had to, let me use this color here. We had to use these placeholders, and then, that was really cool how I did that. Then we also ended up with a remainder, which is different from before. So we have two different things. So what does this remainder mean? Well, what it means is that x minus 3 does not evenly divide into x cubed plus 15. And there's this very important, this remainder it tells us something important. Basically what it tells us is that x minus 3 is not a factor of x cubed plus 15. But there's something else, and that can be summed up here in this next slide. So two things. It's called the factor and remainder theorems. They're basically the same thing. And what it means is this: if p of x is a polynomial and p of a is equal to 0, that means that x minus a is a factor of p of x. Another way to say that is that if the polynomial x minus a divides p of x evenly, that is with no remainder, then P of A is equal to 0. Now we can think about what that means as far as our Desmos graph from before. If we had when we divided f of x by x minus 3, we got this here, and what that meant was that this x minus 3 was a 0 of the original polynomial, and it was, right? It was a factor of the original polynomial. In fact, it was a part where if I plugged 3 into that original polynomial, I would get 0 out. If I plugged in, so we look at this is the factored polynomial. If I plugged 2 into this original, negative 2 into this original polynomial, I would get 0 out. If I plugged in 3, I would get, I said 3. If I plugged in 1, I would get 0 out. If I plugged in negative 3, I would also get 0 out. And so that is what the factor of theorem tells us. It says that if we can divide something evenly, if we can divide a larger polynomial, higher degree polynomial by a linear term, and get 0 and get no remainder, that means that that linear term is a factor of the original polynomial. This is really important. The opposite is also true. If p of x is divided by x minus a and there's a remainder, then it's not a factor, but also it tells us this interesting piece of information here, that the remainder is equal to p of a, or that is, if I were to evaluate that original function for a, I would get the remainder. So let's actually look at that. Let's look at an example of that. So we did this already. We did this problem here. We determined that x minus 4 was a factor of 2x cubed minus x squared minus 22x. What the factor theorem tells us is that if I were to plug in, I don't know what's going on. If I were to plug in 4 into this polynomial, so let's say this is p of x now. If I were to plug 4 in for p of x, this would be 2 times 4 cubed minus 4 squared minus 22 times 4 minus 24. We should expect the answer to be 0. And it should be 2 times 64, right? 4 cubed is 64, minus 4 squared, which is 16, minus 22 times 4, which is negative 88. Minus 24, hopefully this ends up being 0, so 164 times 2 is 128, but minus 88, that would give us 40, right? Then minus 16 minus 24, that's also 40, so this would just be 0. And so that's proof that that works, and you can see it on this next one too. If we said that this was now p of x, and we plugged 3 into that, we'd have negative, so actually 3, right? Because x minus a is equal to x minus 3, right? So p of 3 in this case, p of 3 would be negative 3 to the 4th power. Well, I gotta get off this pen because it's doing all kinds of trick stuff. I'm gonna get rid of that now. Oh, it's not going away. Okay, p of 3 would be, I did it again, 3 cubed, 3 to the 4th, sorry, plus 3 squared, 3 cubed, minus 11 times 3 squared, minus 9 times 3, plus 18. So, okay, 3 to the 4th is 81, plus 27 is 3 cubed, minus 3 squared is 9 times 11, so minus 99, minus 9 times 3, which is 27, minus 18. So 27 and 27, we've got 81 minus 99 is equal to 0. So p of 3 is 0. That's what we expect based on the factor theorem. And the remainder theorem then would tell us for this problem, if I found that the remainder here was negative 12. So if I were to plug in negative 12 to this, so if I plugged in if I plugged in 3 to this, right, x cubed plus 15, that's your p of x. If you were to evaluate this for p of 3, you should get an answer of negative 12. So 3 times, I see I actually made an error in this original problem. So if we go back here, this here should not be negative, right? That should be, we gotta redo this whole part. So we shouldn't get the answer of 12. We should get something else. So it was positive 3x squared, so that should be positive 3x. That would be positive 3x. That would be negative 9x. Then we'd have down here a 9x plus a 15. And then we'd ask, okay, it goes in positive 9 times, so that'd be 9x minus 27. We subtract these, we get an answer of 15 plus 27. That makes more sense. That is 42. And so then if we plug in p of 3 over here, we would have 27, which is 3 cubed plus 15, or again, we'd have 42, which is, of course, the answer to everything. So why is this useful to us? Well, it prevents us from it helps us from having to do horrible long division problems. Like if I was asked what's the remainder when I divide this polynomial f of x, which is 2x to the fifth minus 3x to the fourth plus 2x squared plus 5x minus 6, if I divided that by x minus 4, like I could do it with long division, but it would take forever. So if I just wanted to know what the remainder is, all I would have to do is plug in 4. Right? Because again, x minus 4 is like x minus a, so a would be plugging in would be 4. So we'd have 2 times 4 to the 5th power minus 3 times 4 to the 4th power plus 2 times 4 squared plus 5 times 4 minus 6. And I don't know what this is. I should have chosen an easier number. 4 to the 5th is something big. Let me actually calculate this right now. 4 to the 5th power is 1024. So this would be 2 times 1024 minus 3 times 4 to the 4th power, then would be 256, plus 2 times 4 squared, which is 16, plus 5 times 4, which would be 20, minus 6. And if we subtract these things, sure enough, well, actually, I don't know what the answer is. I shouldn't say sure enough. That'd be 2048 minus 3 times 256 plus 32 plus 20 minus 6. The answer to this is 1,326. So if you plugged in 4 into that function, you get 1326. That's the remainder when you divide. The next problem here, if we wanted to know if is x plus 2 a factor of f of x is equal to x cubed plus 4x squared plus x minus 6, well, we could solve that easily by so this is x minus a. That means a is equal to negative 2. So I want to know what is f of negative 2. So I would say it's negative 2 cubed plus 4 times negative 2 squared plus negative 2 minus 6. So that would be negative 8. Negative 2 squared, so this is plus 16, minus 2, minus 6, and look, this is equal to 0. So it's true that x plus 2 is, yes, x plus 2 is a factor. And so that way we could do that without even having to do any division whatsoever. So that is polynomial long division and the factor and remainder theorems.